Hey everybody, welcome to another edition of Probably Private. I'm Catherine Jarmal, and today we're going to dive even deeper into how do we do differential privacy in deep learning. Today what we're going to talk about is parameter choice, and then what we call accounting. What is that? And then the importance of auditing, along with a little bit of a wish list from me. And this is all related to how do we think about the problem of memorization in deep learning systems, which we know happens when we have novel examples, complex examples. It also happens when we have highly repeated examples or duplication. And it definitely happens when we have super large models, which we have in a lot of cases today. And differential privacy is one of the potential solutions to remove some of that memorization, or at least to be able to decide how do we tune away how much we want to memorize and how much we're able to not learn in the first place when we use differential privacy during training. Okay, so if you're just, by the way, catching up with the series, I'll put a link to the previous videos on differential privacy. When we use differential privacy, what you've learned if you've looked at the other videos is we kind of choose a parameter called Epsilon. This chart is by Damien Desfontaines, and Damien built this beautiful chart. I'll talk about his work a little bit later when we get to auditing, but this chart is an amazing, I think, view of what we call very advanced attacks. So this is an advanced attacker in a potentially worst case situation. What can they actually learn from Epsilon? And Epsilon, which you might recall from the introductory video, is a parameter that we can choose for differential privacy. And in deep learning, we usually use epsilon delta or something called alpha, which is essentially a coupling of epsilon and delta for a particular distribution. And so regardless of what definition you're using, you can usually reverse what epsilon. And this is a good chart, I think, for dealing with multiple stakeholders, so both technical and non-technical people, where you can start thinking about, okay, if I choose an epsilon of 4, what does that actually mean about how much can be learned? And this is a Bayesian-based attacker, and we have an initial suspicion across the x-axis and an updated suspicion. So based on what you told me after I asked you something, this is how much more sure I can be, let's say, that that person's in the data set. And so we can see here epsilons of up to maybe about 3 have a much tighter bounds, and as we get beyond 7, we have a much less control on the bounds. Now, in deep learning, we often use higher epsilons, and it's been proven in research that even under relatively high epsilons, like even epsilon of 8, that it significantly reduces memorization. And this is because you need to think of this amount of information leaking to wherever the differential privacy is being used. In the case of machine learning, the differential privacy is being used to update the model weights. And so this information is going into the model weights. Well, the attacker can't exactly query the model weights one update at a time, or usually can't. And so this means some of the ability to unlock this level of querying gets lost when we think about deep learning. Of course, regardless of where you're using your epsilon, it's good to think about epsilon choice and to reason about it with a multiple stakeholder team and to maybe experiment and choose what's going to be the right amount of balance for whatever it is that you're working on. And that takes us to the moments accountant. So when we're doing deep learning, we use something called a moments accountant. Most of the deep learning libraries have some version of this, including Jack's Privacy or Opacus, which we've already talked about. But you're going to have some sort of DP SGD mini batch step. This is presuming you're using one of those libraries, right? If you're doing your own implementation for a different type of model architecture, you're going to have to implement this stuff yourself, right? But we're going to have some sort of mini batch step. And when we do that, we actually create, in most cases, a Gaussian distribution. And when we create this on the mini batch level, this is tuned using the epsilon and delta that we have, but it's also tuned using some of the properties of that mini batch. And because it's tuned like that, we sample at that point in time what are called higher order moments. So for a Gaussian distribution, the higher order moments can tell us things about the skewness and the kurtosis, basically kind of the properties of the shaping of the distribution. And why do we care about that? Why is that important? Especially these higher order moments, which kind of tell us these higher order properties of the distribution beyond just the mean and the standard deviation. Well, it's because of this chart that I'm showing you here. This is Laplace and Gaussian noise. And these are both tuned, let's say, to epsilon 0.9. So this is an example of what you might be sampling from at that epsilon level for one query, right? And what we can see is that the Laplace distribution has these very exponential properties, and the chance of choosing something close to the real number, so we're adding zero noise, is of course much higher. But then, of course, because it's differential privacy, we have a chance of choosing something else. And the beauty of differential privacy is as long as we don't know exactly what this noise distribution looks like exactly, and we don't know where we then sampled, then we provide essentially that secrecy guarantee for that step of the process, which provides the guarantees for the privacy overall. So I can't reverse engineer what got chosen. And for a Gaussian distribution, we have it kind of like this, right? And for a mini batch, then I'm sampling from somewhere there. But the difficult thing for a long time in deep learning was, how do we then establish rigorous bounds? We kind of need to know, what's the chance that I'm in the middle? What's the chance that I'm near the outsides? And reason about that so that I can think in, again, like Damien's graph, I can think in this bounded accounting, right? At the end of the day, to decide, okay, at the end of the process, what epsilon do we end up with? And so these higher order moments allow us to reason or create better bounds for using Gaussian noise. And Gaussian noise is preferred because it is what we expect a lot of times in our data collection. So of the normal distribution, right? And then also a lot of the ways that we do machine learning lend themselves to Gaussian understanding of error. So that happens at the mini batch level. Then we essentially, in our accountant, we have kind of stored from the mini batches these moments, right, for the different mini batches that got ran. Not the noise itself, just these moments, right? And then at the end of the epoch, we use those collected moments to calculate, based off of a bunch of work that people have done improving this, to calculate that upper bounds. What's the worst case scenario that we leaked when we did all of those gradient updates? And then that gets added to our budget. So again, the budget is then updated at the end of an epoch. And when the budget is reached, we should stop training. Now, depending on what library you're using or if you're implementing your own, there are definitely ways where you can say, okay, I set the absolute ceiling here, but here's my ideal budget. And you can kind of continue training if, let's say, the loss on your problem is still high. So you still are motivated to keep training. This is something that you can do. And so hopefully this helps you start to think about, okay, why is it that we have this moments accountant? What is it doing? And if you're a machine learning person like me, then this starts to maybe help give you a game plan for your initial approach to accounting and using a differential privacy library in deep learning, where you start to say, okay, maybe in the beginning, I set a little bit of a higher budget, and then I use other techniques for early stopping if I hit target accuracy and I haven't spent that higher budget yet. And then still, whatever library I'm using is going to tell me how much did we actually spend from an accounting point of view of my privacy budget, and then what is the model performance results that we got in our, false positive, true positive rates, or whatever we're trying to optimize for from an accuracy perspective. Okay. And then you might be like, wow, this sounds complicated. Somebody has to do all that stuff, like implement it into Opacus and Jack's privacy, or if you're doing it yourself, whatever it is you're doing. And that sounds hard, and it is hard. And this is why I'm showing this paper from Tremer in 2022, which basically there was a breakthrough paper that said, oh, actually, we can do differential privacy in machine learning for much, much less epsilon than previously shown. And these researchers got interested in the paper, and they ran actually, again, some MIA attacks. And as you might remember from the membership inference attacks, if not, check out the video. As you might remember, this involves essentially trying to figure out via whatever query mechanism you're using. I believe in this case, it was querying the gradient updates of these mini batches, and then deciding, okay, do I think this is with or without this example? And they sent some canary examples, some poisoning examples, and they were able to very clearly delineate the difference between the canaries they had and then the average example, right? And these canaries, I think they used a few canary approaches, but some are like random noise, some are mislabeled, some I think that were carefully crafted. But the ability to separate these means that the epsilon that they said they were using was not at all the real epsilon, because we can actually use the properties of these MIAs to calculate the bounds on the epsilon. And so what actually happened here is they said, we think the epsilon's more like this, but you say your epsilon's like that. They dug into the code of the implementation. They found an error with how the gradient norm was used to create the noise distribution and calculate what was appropriate. They found an error in that, which is essentially the sensitivity, if you work in differential privacy. They found a bug in that, and then they were able to send a request to fix the bug. And then, of course, when it reran, of course, it had a much higher epsilon with this sensitivity bug fixed. Now, I mentioned all this. I'm going to link a few really great articles on auditing, both for deep learning. I'll link this paper, but I also want to say that Damien, whose work has inspired a lot of learning from me, also does a lot of these cool auditing for things outside of machine learning or in machine learning, and I'll link his services. So if you're building your own differential privacy library, I can recommend using his services, but you can also use somebody that is, again, a deep expert in differential privacy, and then have that person independently audit or pay a group to independently audit your implementation, because it's just what we know also from cryptography is that even smart people, even domain experts in certain parts of the space, especially if it's your first time implementing differential privacy, you can actually make a lot of errors, right? And so this is why it's really good to have peer review. This is why I support open source code that can be peer reviewed, but also make sure that you use independent auditing if you're building your own library. Now, going back to the machine learning people, so if you're not also building a library, you might be curious, can you run these MIAs? Can you get an idea of what's happening during training? The answer is yes. There's some ways already to do this, I think, in Jack's privacy. There's also some really cool new types of approaches, and this is one I really, really liked that came out in 2025, where they essentially collected the loss distributions. So instead of using the distributions based on the attack, they used just the distributions that we already know based on example level loss, and they were able to find examples that were prone to MIAs just by looking at the distribution of the loss and saying, this loss doesn't look like the other losses. And that kind of relates to a lot of what we've been talking about. Why does memorization happen? It happens because either something is very complex, it has high information, and so the model decides, this has a lot of information, I'm going to save it. Or it's very unique, but still worthy of learning. And so when we see this with their chart of the loss over a period of epochs, we can see that the average frog in the purple, it gets learned very quickly. So it gets learned in, epoch number, I don't know, maybe 2 or 1. It gets learned very quickly, average case, and then the loss drops and it holds low, right? We can see the easy to fit outlier, which actually in their MIAs was the most vulnerable to attacks. Of course, as you hopefully know from reading the article series and being here, that can vary depending on your task and depending on your data set. But for their task and data set, which is CFAR 10 and some sort of computer vision architecture, they see that the loss increased, drop, and then by about 40 epochs, there was another last little spike, and then it settled down, right? And so that loss distribution for that example has different properties. And then we can see for the hard to fit outlier, which is kind of this grainy frog, doesn't look a lot color differentiated from the background, that this was less vulnerable to MIAs. Maybe because it never got fully learned, right? They did 100 epochs, and we can see that when they ended, it still had a non-zero loss, obviously. And this one we see also is very spiky, right? It's clearly either warring with other examples that have different information that's worthy of saving, or it's also just hard to fit based on whatever model architecture they used. But what they found, again, is that these loss properties share a little bit of a hint at what might be wrong from a privacy attack perspective. And also just in general might help show us as machine learning people, do I actually want to learn this example or not? Especially when learning this example might mean memorizing this example. And so I am looking forward to hopefully seeing stuff like this be implemented into ML ops, things like weights and biases, or other things like this, where we can choose to say, okay, randomly sample, or I want you to overly sample from these types of examples. I want you to track the loss, and then I want you to show me interfaces like this while I'm training. So I, as machine learning engineer, can start to be like, is it actually learning the way I want it to learn and what I want it to learn? Which I think would be very useful for privacy, especially in these types of things. So what I want to see is more of this thinking of how do we test during training and how do we implement this as kind of a cheap test compared to a handcrafted MIA. Of course, a handcrafted MIA tells us a lot more about privacy leakage, but this is kind of a cheap way to say, okay, I know I'm having at least this much memorization, and then it's probably beyond that. And then finally, we need more examples. We need more people using and adjusting differential privacy for different tasks. As you might remember from the initial video on this, if you craft differential privacy for your task, you're going to get a lot better results, both from privacy guarantees, but also from utility. So how accurate is your model? How performant is it? And so forth. And so the more that we build these out and experiment, the easier it will be, again, for other people coming after you to learn, oh, interesting, they had this model problem, they had this model architecture, here's the libraries that they use for differential privacy. Maybe I'll try that. Or maybe now that we know this new thing from other people publishing their results, maybe I'll try it this way this time or that way this time, right? And the more of those, even outside of research, I think the more that we have from industry, the better also for researchers. We need realistic data sets and large-scale setups. So quite a bit of the research, because people are compute constrained and cost constrained and probably also time constrained, we have, the same data sets again and again. And they're pretty small models compared to a lot of the models that we actually are using today. And so the more that we can encourage more realistic data sets and more large-scale setups, the better that we can do. More links on that in the longer article. We need better libraries for attacks. We need better libraries for at-risk example detection during pre-processing. We could probably even do it before we start processing, depending on how complex our data or task is, and certainly when we're doing training. And we need more people using and requesting models trained with differential privacy. So again, I already highlighted Vault Gemma, but hopefully there's others that you can share. If you just released one that you want people to test out, put it in the comments. Let's try to support the ability to use models that are built with more privacy thinking, with more privacy built in. And if you're curious to learn more, I wrote a book of which obviously some of the chapters are exactly about differential privacy and deep learning. So you can check it out. It might even be available for a free loan from your local library. And it's in also German and Polish alongside English. So I hope you enjoyed this. Maybe I inspired some new ways that you're going to test and work with differential privacy. If you have other questions, let me know, because we're going to move on to other ways for us to think about memorization. This is kind of the last for now in differential privacy and deep learning. And I'm excited to hear your thoughts in the comments, or also you can always ping me via email. And I'll see you next time, where we might be exploring some ways that we can think through model minimization, but with attention to privacy. All right, see you then.